Lecture 30 is P4GM. So what we've done is, you recall that we had previously added the M to the, we had previously taken the point group of 4 and added M to it and gotten 4MM and then put that into the lattice. Here, we're going to take the point group 4, which is in the lattice, so we'll have a P4. And just like we did, we're going to do an offset addition of G and see what that does. So let's draw that. P4 is compatible with a square lattice, so hopefully this is a square lattice. And you recall P4 had, of course, fourfold axes at the lattice sites. There's A pi's in there. So the bisectors, recall that we knew we're going to have these guys. And that the same theorem for a fourfold axis here produced one in the middle. And without any mirror planes, that was P4. Now, let's do the same thing we did with P2. Delta here. So of course, we're going to induce and so for sure, if you slip in these G's, right, based on the twofold theorem, we're going to end up with these guys by our theorem, just like P2GG. And these are all identical. They're all identical G's. Now, we didn't develop a theorem, I don't believe, for this, but, and we could probably, but let's put in our P4, making sure I get all the handedness correct. This has to be the same. I didn't draw it exactly the same. Okay, so there we have our lattice sites that have the fourfold symmetry. Now I induced these, right? So if we, actually let's keep the same color. If we, let's say, flip this one around here, I'm going to have something like that. And then I'm going to translate down. So again, it's kind of above that one there. So it's going to be above this one like this, and I translate down. So it's going to be more or less the opposite handedness of that one, right? Same thing here. If I flip this one around that mirror plane, it's going to end up being over here and like that. And so this is going to go here. And so on. So you can see with this fourfold axis, you can see what's going to happen. All those produce things that look like this. What that means is by me putting these in, it's induced the opposite handedness of the fourfold axis in the middle here. Now to prove that these exist, we can do what we did before, which is that if I, for example, flip this one around there, then translate, I end up with that guy. So it proves again, that I have that. And of course I can flip up over here and I end up with, that guy. So indeed, our theorem, which says that these guys have to be here, they're there. What we didn't have a theorem for was, if you'll notice, this one is reflected over here, this one is reflected over there, if I drew it correctly. And so what um, we never developed a theorem for, but is shown here, is we have mirror lines passing through there. And you know what happens when we have translation vectors that are at angles there? We should actually induce more glide planes. And let's see, if we had a glide plane we would think that would pass through the middle here, then what that would mean is that, if I can draw this correctly, I would flip this one over here, which would be something like that, and then it would translate down to here. Right, so let's show you that. This guy, if there was one running in the middle, would flip over here and kind of look like that. Then if I translate over to here, it produces that. So you can see, indeed, it is there. An example here would be this one will flip across, producing something that would look like that. This one flip across there, and that would go here. So what it suggests is that once I recognize I have those red lines, it produces glide planes in the middle from our other theorem, where we have two parallel ones that are at incline to the translation vectors. And there you have P4MM. The distinguishing feature is that the corners have the same, of course, motif, but then the inside one has the mirror image of each one of these in the center.